In this video, we're going to focus on perpendicular bisectors. So what exactly is a perpendicular bisector? So here's the gist of the definition. The perpendicular bisector is a line that bisects a segment into two equal parts and is perpendicular to that segment. So consider the segment AB. So this is point A and this is point B. And we're going to draw a line that passes through the middle of that segment. And let's call this line L. Let me use a different color. Now for L to be a perpendicular bisector of segment AB, or rather, let's call this point where it intersects point M. So AM has to be congruent to BM. It has to bisect segment AB into two congruent parts. So AM is congruent to BM, which means that point M is the midpoint of segment AB. Now, a perpendicular bisector is also perpendicular to the segment, so it forms right angles. So this is also a right angle as well. So we could say that line L is the perpendicular bisector of AB. So for two-column proofs, you might be using this symbol here. Now what about the perpendicular bisector theorem? It states that if a point is on the perpendicular bisector of a segment, so that would be point P, then it is equidistant from the endpoints of that segment. The endpoints of the segment are A and B. So therefore, PA is congruent to PB. Now we can place the point anywhere along the perpendicular bisector line. So for example, we could say point Q is equidistant. Let me put this below it so it doesn't overlap with the line. Point Q is equidistant to points A and B. So these two sides are also congruent. So therefore, QA is congruent to QB. And so that's the main idea behind the perpendicular bisector theorem. Now there's another version of this theorem which states that if two points P and Q, are equidistant from to the endpoints of the segment, that's A and B, then those 2 points determine the perpendicular bisector of that segment. So we can also say that line PQ is the perpendicular bisector of segment AB. Now consider this acute triangle. Draw the 3 perpendicular bisectors of this acute triangle and determine the location of the circumcenter. The circumcenter is where all 3 perpendicular bisectors meet up. So if you want to determine the circumcenter, first identify the 3 midpoints of each side. So let's say this is triangle ABC. The midpoint to AB is somewhere over there. The more accurate you can place the point, the better the picture will be. The midpoint of AC is somewhere in that vicinity, and BC is around here. Now what you want to do is draw a perpendicular line to each of those points. So for AC, a perpendicular line would go straight down. It has to pass through the midpoint of each segment or each side of the triangle, and at the same time it has to be perpendicular to it. It has to form a right angle. So these 2 sides must be congruent. Now to draw the perpendicular bisector of BC, we need to draw a line perpendicular to it. The line doesn't have to pass through the vertex. So these two sides are congruent, and this forms a right angle. And now for the third side, it has to be like this. So I don't have a ruler, my lines are not perfectly straight. So I'm basically eyeballing it. So this is another right angle. As you can see, they intersect at a common point. So that point of intersection is known as the circumcenter. And it turns out that if you draw a circle that touches the three vertex of the triangle, the circumcenter is the center of that circle. So let's see if my drawing skills are somewhere okay. So you can see that this is the center of the circle. Now my circle is not perfect, but you get the point. So what you need to keep in mind is that the circumcenter lies on the inside of an acute triangle. For a right triangle, it lies on the hypotenuse of a right triangle. In fact, it's on the midpoint on the hypotenuse of the right triangle. And for an obtuse triangle, the circumcenter is located outside of the obtuse triangle. So let's look at a right triangle. So let's say this triangle is triangle ABC. Now identify the midpoints of each side of this triangle. So we have a midpoint here, a midpoint that's about here, and another midpoint that's in this vicinity. And then draw three perpendicular lines. So perpendicular to AB is a line that looks like this. Perpendicular to BC is a line that looks like that. And perpendicular to AC is a line that looks like this. So as you can see, they intersect on the hypotenuse. And in fact, they intersect at the midpoint of the hypotenuse, which means that this side is congruent to that side. So if we call this point M, AM is congruent to CM. Now let's draw the circle that passes through all 3 points. Let me start with point A. As you can see, the circumcenter is in the midpoint of the circle. It's at the center of the circle that we just drew. Now let's draw an obtuse triangle. And let's call it triangle ABC. So go ahead and identify the location of the circumcenter. So to do that, identify the midpoint of BC, AB, and AC. So let's draw the perpendicular bisector of BC. And then let's do the same for AC. So it should be something that looks like this. So make sure that it's a right angle. It doesn't have to be perfect, but if it's good enough, then you should be fine. So that's the third perpendicular bisector. And as we can see, they meet at that location. So the circumcenter is outside of an obtuse triangle. So now let's draw the circle. So draw a circle that touches points A, B, and C. This might be a little tough. Let's do that one more time. Okay, you get the picture. So as you can see, the circumcenter is approximately at the center, well, it should be at the center of the circle that we just drew. Now let's work on a 2-column proof. So let's call this A, B, C, and D. And we're given that AD is congruent to CD. And also that B is the midpoint of AC. Our goal is to prove that line BD, or line DB, is the perpendicular bisector of segment AC. So go ahead and do a 2-column proof to show it. So how can we do this? In order to prove that BD is the perpendicular bisector of AC, we need to show that points D and B are equidistant from the endpoints of the segment A and C. Now, if you recall, according to the perpendicular bisector theorem, it states that if 2 points are equidistant from the endpoints of a segment, then those 2 points determine the perpendicular bisector. So we got to show that D is equidistant from A and C, and B is equidistant from A and C as well. So let's start with the first statement, that AD is congruent to CD. So if AD is congruent to CD, that means D is equidistant from A and C. So I'm going to put a dot to show that this statement proves that D is equidistant from the endpoints of the segment AC. And this statement was given to us. Now the second thing that we know is that B is the midpoint of segment AC. So that fact was given to us as well. So now we can move on to step 3. If B is the midpoint, what conclusions can we draw? If B is the midpoint, then AB is congruent to BC. So AB is congruent to CB, and that's based on the definition of a midpoint. So now, step 4. Oh, by the way, since AB is congruent to CB, that means that B is equidistant from AC. So now that we have 2 points that are equidistant from the endpoints of segment AC, we can make the final statement that, which I'm going to put over here. So the final statement is that line DB, or line BD, is perpendicular, or is the perpendicular bisector of segment AC. And what can we put for the reason? This is based on the perpendicular bisector theorem. And remember, the perpendicular bisector theorem states that, at least a form of it states that, if 2 points are equidistant from the endpoints of a segment, then those 2 points, which are D and B, they determine the perpendicular bisector of that segment. Let's look at another example. Let's say this is point A, B, C, D, and point E. Given that AD is the perpendicular bisector of segment BC, prove that triangle ABE is congruent to triangle C, or rather ACE. So we need to prove that this triangle is congruent to that triangle. How can we do so? Well, let's start with a 2-column proof. So in this example, we're given that line AD is the perpendicular bisector of segment BC. And so that's given. Now what can we conclude from this? Now remember the definition, or the perpendicular bisector theorem, which states that if a point lies on the perpendicular bisector, that point is equidistant to the endpoints of the segment. So let's look at point A. Point A is on the perpendicular bisector. So that means that it's equidistant to the endpoints of segment BC. So we could say that AB is congruent to CB based on the perpendicular bisector theorem. So now let's mark the graph. Now notice that E is also on the perpendicular line, or the perpendicular bisector. So E is equidistant from BC. So we could say that segment EB is also congruent to EC according to the perpendicular bisector theorem. Now number 4. So BE and EC are congruent. So now we can say that AE is a common side to those two triangles. So AE is congruent to itself based on the reflexive property. So now in step 5, we could say that triangle ABE is congruent to triangle ACE. And this is based on the side-side-side postulate. And we've used statements 2, 3, and 4 to arrive to that conclusion. And so that's how you can use the perpendicular bisector theorem to establish that certain segments are congruent in a 2-column proof. Now we're going to consider one more example. You need to know when to use the definition of the perpendicular bisector and when you need to use the perpendicular bisector theorem. So this example will illustrate that. So let's say that DB is the perpendicular bisector of segment AC. So with that information, I want you to prove that triangle ABD is congruent to triangle CBD. So let's start with what we're given. Line DB is the perpendicular bisector of AC. So what do we know about perpendicular bisectors? They form right angles and they bisect the segment into 2 congruent parts. And that's basically the definition of a perpendicular bisector. So anytime you need to prove that it bisects a segment into 2 parts, or that it forms right angles, your reason is the definition of a perpendicular bisector. And so we could say that AB is congruent to CB. So now let's move on to step 3. We do have a common side, so we could say that BD is congruent to itself based on the reflexive property. Now notice that D is on the perpendicular bisector, which means that it's equidistant to the endpoints of the segment. So we could say that AD is congruent to CD. And this is when you need to use the perpendicular bisector theorem. You can also write it as a sentence if you want. So anytime you have a point that is on the perpendicular bisector, that point is equidistant to the endpoints of the segment. So AD is equal to CD. So now all three sides are congruent. So in step 5, we could say that triangle ABD is congruent to triangle CBD. And this is the side-side-side postulate. And we use statements 2, 3, and 4. And so that's it for this proof. So if you want to use definition of the perpendicular bisector, that's to prove that the two segments are congruent or that right angles are formed. Now, if you want to use the perpendicular bisector theorem, it's to show that D is equidistant from A and C, which means that AD is congruent to DC. Or if you have some point in the middle, let's say point F, you could say that AF is congruent to CF because F is on a perpendicular bisector. So any point on a perpendicular bisector is equidistant to the endpoints of that segment based on the perpendicular bisector theorem.